The Monty Hall problem is a very interesting probability puzzle. The puzzle originated from this famous TV show called Let's Make a Deal, which started in the 60s in the US. Its host, Monty Hall, used to play mind games with the audience and the participants.
We'll find out right now when we turn over the last price, and it's right!
Very good. You put your confidence in the right young lady. There she is. Do you remember 3 minutes ago, this is the kid that didn't even know her own name? Boy, does she come through at the end with a brand new automobile with our congratulations.
Alright, great. Let's now deal with the puzzle. Let's say that there are 3 items that can be won in a game. A car and 2 X's. So these X's mean that the participant either wins nothing or what they win is not comparable to the main prize, which is the car. In the puzzle itself, there were 2 goats instead of the X's, but since I like goats, I substituted them with X's. Now, these items are hidden behind 3 doors, and we do not know which door contains the prize. Let's say that I pick door number 1. Here comes the Monty Hall into play, where he opens the door, shows me that the car is not behind this door. Now he asks me, would you like to switch or stay with your current choice? You can also pause the video and ask yourself, which would be better, to stay or to switch? To answer the puzzle, it would be a good idea that we analyze all of the possible situations. In a typical game, there are 3 doors and door number 1 is the choice at the moment. So, there are only 3 scenarios that are possible. In the first one, the car would be behind door number 1. In this case, after Monty opens one door and shows that the car is not behind it, it would be wise to stay with the original choice. Switching will mean losing here. The car in the second scenario would be behind door number 2. In this case, after Monty shows door number 3 and shows that there does not exist any cars behind it, it would be better to switch. Staying with the original choice would mean losing here. Similarly, in the final possibility, the car would be behind door number 3, and exactly like the second scenario, it would be better to switch here as well. So we can see that staying wins with a probability of 1/3, while switching will win with a probability of 2/3. So it would be definitely better to switch. This solution was originally made by Marilyn von Savant. So how can such games be simulated? Well, easily. There are 3 possible values and a game can be implemented like this. First, begin by taking a sample of the values and do this without replacement. It would then be exactly the same as shuffling the original values. Then mark the participant's choice. This can be done using the modules of the random library in Python. Now remove one of the X's. It does not matter at all which one is removed because the position of the doors is not relevant and we just care about switching or staying. Finally, check which option would have been better for this game, switching or staying. I have already imported the random library and have also defined the total number of games. The list of all possible values and also the counters for staying and switching have been initialized as well. As the final step, the results should be printed out to the console. We are interested in knowing the percentage of the games that would be won based on staying or switching. Now let's test it. As you can see, after generating 100,000 games, around 1/3 of them have been won by staying and 2/3 have been won by switching. Perfect. Now with that, this video comes to an end. You will find the link to the codes in the captions of the video. Thanks a lot for watching and see you in my next video.